Hello, welcome to the Pre-Calc Chapter 1 review. What I'll do is give you a brief overview of some of the questions I'll go through in this video. First one we'll do is talk about slope-intercept form, about perpendicular lines, and then we'll talk about domain of square root functions and some of these rational functions. We'll look at compositions of and operations of functions, graphing a system of linear inequalities and determining if a point is a solution. We'll graph a linear piecewise function and then do a regression problem on the calculator. So I'll start with writing the equation in slope-intercept form of a line that passes through the point -3, 4 and is also perpendicular to this line below. So what I want to do first is determine the slope of this line. I'm going to subtract 2x on both sides to basically try to isolate y. So I'm going to end up with this. And then what I want to do is divide everything by -1, and what that's going to do is get my y all by itself. So y equals, I have a negative over a negative, so this is positive 2x and then minus 6. So the only piece that I really need from this is that my slope is 2 over 1. So what I want to do is get the perpendicular slope to this, which is going to be an opposite reciprocal. So I'm going to flip the fraction, so it's going to be 1 over 2, and then opposite meaning first positive, now it'll be negative. So what I want to do is write the equation of a line that has this slope that passes through this point. So I'm going to do a little substitution. I'm going to basically use slope-intercept form and find my y-intercept using that point and slope. So I'm going to substitute 4 for y. I'm going to substitute -1/2 for m. My -3 for my x value, and then we'll find the y-intercept of this. So 4 equals -0.5 times -3 is positive 1.5 plus b. So I'm going to subtract the 1.5 on both sides and get a y-intercept of 2.5. So at the very end of this, I know that my perpendicular line is going to have this slope and this y-intercept. So I can say y equals my m x plus my b. Alright, if it would have said parallel, you would have, so that's the only difference really, you would have used a slope of 2 over 1 as well, and done the same thing over here to determine the y-intercept. On this next one, we're going to talk about domain of these following graphs. So if I were to graph the square root of x plus 2, what would happen is, if you put this in your calculator, you would see a graph that would look something like this. And what it means is any value, any x value to the left of this, if you substitute an x value into this square root, you would have a negative number plus 2, and you would end up with the square root of a negative, which would yield a solution that is not real. So our domain would be anything starting here for x values all the way to the right. So my domain is going to be all my x values that are greater than or equal to -2. So the way that you can algebraically do that is to take the inside of your square root function, whatever we refer to this as the argument of the function, and you could take that, and because we know the inside of the square root has to be positive, I'm going to just put greater than or equal to 0. Solve this by adding 6 and then dividing by 2. And that would be just an easier way of just saying, okay, my domain is all of my numbers, all my x values that are greater than or equal to +3. So that's a different type of function than the one that's below, which, again, if you were to graph the one below, you would end up with some sort of little curvy thing like this, and you would end up with a vertical asymptote within your graph. What that means is every x value is going to work except for, in this case, one x value would turn my denominator into 0. So you want to know what x value turns your denominator to 0, because if you divide by 0, you would end up with an undefined value. So my domain is going to be all real numbers, except x will not be, in this case, one number. So to figure out what that number is, all I'm going to do is take 2x minus 1 equals 0, add 1, and divide by 2. What this tells me is x cannot be a half. If x is 1/2, what would happen is this denominator would turn to 0, and I would end up with a value divided by 0, which is undefined. You could pick any other number, Any ugly decimal, any negative number, you could pick 0, you could pick anything, and it would at least give you a y value. So in this case, again, my domain would be everything except 1/2. For the one on the right, you would have a graph where there's going to be a couple x values that would not be included within our domain. So again, I'm going to write down it's going to be all real numbers, except x is not going to be a couple things. So I'm going to take my x minus 4 and set that equal to 0, and I'll take my 3x plus 3 and set that equal to 0. And this is something that is a review. This is the bottom part represents a quadratic graph, which means we would have these like two values that would turn my denominator, in this case, into 0. So I'm going to add 4 here, and then I'll solve this one by subtracting 3 and dividing by 3. And what that tells me again is if x is either of these two values, my entire denominator would turn to 0. So my domain then is saying that x could be anything except those two values. So now we'll take a look at compositions. I have 3 functions up here. The first one's linear, then I have a quadratic, and then a rational function. The first one is asking us to subtract them, which is the same thing as if I were to take my f of x function and subtract the entire g of x function. So I'll do that below. I'm going to take my f of x function, which is 2x plus 3, and then it's very important to take the g of x function and put it in parentheses. Reason for this, I'm going to end up distributing this negative 1 here through the parentheses. So if you would have forgotten these parentheses, you're not going to get this negative times a negative, which would change your answer. So now I'm going to bring this down, distribute my negative 1 through. Negative 1 times 1 will give me positive 1 here. And then I'm just going to combine some like terms and write this in standard form, which would be negative 3x squared plus 2x plus 4. So that'd be your final answer. All we did, again, was just subtract 2 functions. With the next example, we're going to be evaluating a composition for a given input. So start with your inside function. What I'm going to do first is evaluate f of negative 4, which means I'm going to use negative 4 as my input to my f function first. And this is going to give me a number. So that number in this case is going to be negative 5. So using that negative 5 now, I'm going to substitute it into the g function. So I really now want to use g of negative 5. So I'm going to go over to the g function, which is 3x squared minus 1, and I'm going to evaluate that for negative 5. So order of operations would tell me to do the negative 5 times negative 5 first, which is 25. Multiply it by 3, and then subtract 1. And that's going to come out to 74. So again, basically just working your way from the inside out. You could also do a composition of functions first. Like you could do g of f of x first and like take the entire function and just substitute it in for x and then substitute 4 in. But this way also works. You're going to get the same answer. The bottom two, I'm going to do a multiplication and then I will do a composition of 2 functions. So this first one is going to take my h of x function, which is 2x over 3x minus 4. And I'm going to multiply that by my f of x function, which is 2x plus 3. And I'll just rewrite that my denominator in this case really is just 1. So all that you're going to do is just multiply straight across. So on my numerator, the 2x is getting multiplied by this 2x and by the positive 3. So you'll need to distribute. 2x times 2x is 4x squared. And then 2x times positive 3 means I'm adding 6x. My denominator is taking 3x minus 4 times 1, which is just 3x minus 4. And that's it. You're just multiplying 2 functions together. Nothing with like substituting one function in for the other. That's what we're about to do in this last example, which h of g of x is basically saying I'm going to take this entire function, g of x, I'm going to take this part right here, and I'm going to substitute it in for x in both of these places in my h of x function. Okay, so what I'm going to do first is just write my h of x function down, but instead of writing my x's, I'm just going to leave myself some space because I'm going to be substituting an entire function into those parentheses. So again, this is my h of x function. I'm going to bring it down here, except again, I did not write my x's. In for those x's, we are using my g of x function for my input. And I'm going to put that in both of these spots by substituting, and then all you're going to do is simplify. So to simplify my numerator, I'm going to distribute. So I'm going to end up with 6x squared minus 2. And on my denominator, I'm going to distribute this as well. And that'll end up being 9x squared minus 3 minus 4. So what I can do is just clean up that bottom by combining a couple like terms. And my denominator becomes 9x squared minus 7. So again, that's a composition. All four of those, or I should say, 2 of them are compositions, 2 of them just the subtraction and multiplication. We'll move on to inequalities then. So what I'm going to do is look at this system, which one of these is written in slope-intercept form, one of them is written in standard form. So we'll graph this, and then we'll algebraically and graphically be able to identify if this coordinate is actually a solution. So what I'm going to do is take a look at this first inequality, and I'll do all of that work in blue. My slope of that is negative 1 over 2. My y-intercept is positive 4. Because this says less than, it means that I'm going to construct a dashed line, and that any point that is on that line will not satisfy this top inequality. Because it's written in slope-intercept form, and it says less than, I'm going to shade below my graph. So I'll end up graphing that in a minute. Let me get the other one in slope-intercept form. So I'm going to do that first by subtracting 3x on both sides. And then I'm going to need to divide everything by negative 1. By doing that, when you divide by a negative, multiply or divide by a negative coefficient to y, you're going to need to flip your inequality. So now it's going to become greater than or equal to, this will become 3x and then minus 5. So I'll do the same thing. I'll write out my characteristics here. My slope is 3 over 1. My y-intercept will be negative 5. This is going to be a solid line. Because it says greater than or equal to, that means that all the points that are on my line will be solutions to this one inequality. And then because it's in slope-intercept form, and it says greater than, I'm going to shade above this. So let me start this first blue graph with my y-intercept. I'm going to start up 4. I'm going to put a point there and go down 1 and to the right 2 for my slope. Could also go up 1 and to the left 2. And I'm going to construct a dashed line through this, which is going to be pretty ugly. Okay, and then what I'll do is shade, I'll shade below this, which again, this is all indicating what part of my solution would be just for this one inequality. Okay, so now I'm going to do the same thing for my other one. I'm going to start this down 5 for my y-intercept. My slope is up 3 and to the right 1. I could also go down 3 and to the left 1. I'm going to draw a straight line, solid line I should say, through this. And I'm going to shade above that graph. So that's going to be everything on this side. Which, notice that because I use this crazy ugly highlighter, you're going to see this really dark region. That dark region represents the double shaded part of my graph. That is where my solutions will lie. So everything that is just in the blue part is only going to satisfy the top inequality. Everything in the just orange part will only satisfy the bottom. The double shaded region represents the solutions to my overall system. So for example, I could go to the left 3, and at this point negative 3, 0, that's in the double shaded region. That will work for my entire system. It will algebraically satisfy both inequalities. If I take negative 3 and substitute it for x, and if I take 0 and substitute it for y, it will work in both. That's what we're about to do. I'm going to take the system of inequalities, and I'm going to use the point negative 2, 6. Negative 2 being my x value, 6 being my y, and I'm going to substitute it in both of these. So we can see where negative 2, 6 is on my graph. It's going to be up here somewhere, and we'll see if it algebraically satisfies the system. So I'm going to take 6 and substitute it for y in my top inequality. and I'll take negative 2 and substitute that for x. So simplify this. Half, or negative half of negative 2 would be positive 1. So what I'm going to end up with is 6 is less than 5. That is not true, which means automatically, because this one inequality, because this point was not a solution to one of my inequalities, it is not a solution to the entire system. Even if it works for my bottom inequality, it's still not going to be in this double shaded region, therefore it's not a solution to the system. So then the next problem we'll do is graphing a linear piecewise function, which I'm going to break this up in a few different parts. So what I really have here are three different equations of lines, and off to the right here I have the domains that are going to correspond to each of those separate pieces. So what I'm going to do is color code this to my best abilities. Take each of these lines into consideration. What we're going to do is look at the slope and y-intercept of them. I'm going to graph them on here, and then I'll manipulate them after, basically by looking at these pieces of domain. So my first equation up here, if I were to write this like in slope-intercept form, I would say y equals negative x plus 2. Okay, your slope would be negative 1 over 1, and my y-intercept would be positive 2. So what I'm going to do is graph that line using these characteristics of it. I'm going to start up 2 and put a point there, and go down 1 and to the right 1. And similarly, I could go up 1 and to the left 1. So I'm going to construct a line. I'm going to construct a line with those characteristics. And again, that's going to just represent, that's going to represent my first piece of this piecewise function. All right, good enough. So what I'm going to do next then is take a look at, I should not have erased those. Bam. I'm going to take a look at this next graph, and I'll switch color. So I'm going to look at that equation and pretend that it said y equals 1/3 x minus 2. My slope of that line would be 1/3, and my y-intercept would be negative 2. So I'm going to start down 2 for my y-intercept, and I'll go up 1 and to the right 3. And that's going to give me another coordinate. So now I'm going to connect those dots and construct that line. So let me connect the dots here. Okay, so that's going to represent the second piece of my function. And then the third one is just basically y equals 4, which is going to be a horizontal line. So I'm going to go up 4, and I'm going to construct a line there. Going straight across, and I'll do that in green. Alright, so here are my three pieces to my graph, which is going to be split up between these three different domains. The first domain says for any x value that is less than negative 2, that's going to follow my blue function, which means what I'm going to do is take this blue graph, and I'm just going to shrink it down, and I'm going to make it start then at the value of negative 2. However, it says all the values that are less than negative 2, not less than or equal to, which means I'm going to have to put an open dot here, because if I had an x value of negative 2, it would move into my next piece. This one says less than or equal to, so that means that my next piece is going to start, and that's the orange part, that's going to start at an x value of negative 2, and that would have a closed dot on the end. Okay, so this first part was the blue that represents every x value that is less than negative 2 would use this basically would use this first equation here, and you would substitute your x values in to get your y values. The second piece, and I should probably put an arrow on this, the second piece is saying, okay, if you have an x value of negative 2, you're going to start here. Now where you finish on that graph is all the values that are less than 1. And because it says less than, I'm going to need to cut off this orange graph at positive 1. I'm going to shrink this down to where positive 1 is on my x value. And because, again, it says less than, I'm going to need to put an open dot here. So that represents, this little piece says, okay, for any x value between, so just strictly looking at the x-axis, this is negative 2, this is positive 1. Everything in between here is going to use this middle function to get your y values. The third piece is referring to that horizontal line that I have, and that is every x value starting with positive 1, starting with positive 1 and going all the way to the right. So to basically all of your x values going to positive infinity. Those are going to get that green function, which basically just says, hey, your y value is going to be positive 4. So notice that my domain is technically all real numbers. I could take any x value. Okay, I could take negative 5. It would go to this first piece. I could take positive 10. That would go to this bottom piece. I could take 0, which would be in the middle of this graph and would fit for this middle piece. And you could do that for all of these values, and you would always have a corresponding y value. So this is the graph for that piecewise function. The last one is a regression problem. So this is dealing with time that's measured in years, and we're going to be talking about a population of a very small town. We'll make a prediction of that population, and then we'll look approximately when it would reach 4,000. So what I'm going to do is call 1998 my 0 year. That's going to be my initial year. 3 years later would be 2001. Now that's 4 years past that, however, 7 years. Okay, 2005 is 7 years past 1998. 2008 would be exactly 10 years, and then 2012 would be 14 years later. So what I'm going to do is use those values in my calculator. So let me pull up a calculator here. And what I'm going to do is go to Stat, and I'm going to go to Edit. And I'm going to enter in my 0, 3, 7, 10, and 14 for my L1 column. And then for my L2, I'll go ahead and enter all those population values. Which again, population is measured in people. So when I get my regression equation, I'll just round to the nearest person. I also want to make sure, you can do this as well. Well, first of all, let me just get my equation, then we'll see if my R value, which again, that's the correlation coefficient, we'll see if that pops up. So once your data is entered, you go to Stat, you go over to Calculate, and then the fourth option on mine is a linear regression, AX plus B. I'm going to calculate this, and my A value is going to represent the average increase of population per year. The B value represents my approximate population in the year 1998. So my approximate is pretty darn close to the actual. My actual value is 2557. My approximation is 2522. So I'm going to write this equation down. I'll round to the nearest person. So I'll say y equals 48x plus 2522. Oops. Y equals 48x plus 2522. Notice my calculator did not give me an R value. If that's the same case with yours, I'll turn this on right away. I'll press second, and then the number 0. What I'm going to do is hit the alpha key a couple times here. Actually, I don't even think you need to do that. Let me try this again. I'm going to press second and catalog, and right away the alpha key is already defaulted. If I hit this button here, I can see the letter D is right here. I want to find diagnostic on. And that's going to turn on my R value for me, which some of your calculators probably already have this on. Basically now, if I go back to Stat and I recalculate my linear regression equation, it'll give me my correlation coefficient, which I'm going to round this R value to 3 decimals, so 0.973 will be my R value. So because this is a positive correlation, meaning as my time increases, my population will increase, you're going to see a positive number here. Had it been a graph that looked like this, you would see a negative R value, and also a negative slope. So because my R value is pretty close to positive 1, this is a pretty strong correlation. Had this been a number like 0.52 or something, that would have been a pretty weak correlation and maybe not linear for the best, or linear would not be your best model then for that pattern. What we're going to do is use this equation now and predict the population in 2020. So what I want to basically know first of all is if I put 2020 here, what blue value would I have to match up with that? How many years is 2020 past 1998? And that would be 22. So 22 is the input that I'm going to use in my equation. So I'll say y equals 48 times 22 plus 2,522. So because I'm giving you an x value, I'm going to substitute, or because I'm giving you a time value, I'm going to substitute that in for x in my equation. and I'm going to get an approximate population of 3,578 people. The next part is saying approximately when will the population reach 4,000. So if I had a y value of 4,000, I want to know what my corresponding x value is. So I'm going to do the same thing, except this time I'm going to substitute 4,000 in for y, and we need to solve for x. So this is just a linear equation. I'm going to take my 4,000 minus my 2522 and get 1478 equals 48x, and then I'll divide both sides by 48, and I'm going to end up with an x value of 30.79. So that is approximately 30 to 31 years after 1998. So what you would need to do is take 1998 and add approximately, I'll just say approximately 31 years to that. So your answer would be the year, because it says approximately when, so I want to know the year. Approximately 2029, the population would reach 4,000 people. Okay, quick recap. So again, we did linear equations talking about slope and y-intercept and calculating the slope, parallel and perpendicular lines. Went through the domain of two different types of graph, the square root graph and the rational function. We looked at compositions and different operations of various functions and evaluating inputs in different functions. We looked at shading the inequalities and systems of inequalities, looked at like if a point was a solution, and we determined that graphically and algebraically. We looked at graphing a linear piecewise function, which again, I basically just graphed 3 lines and then kind of chopped them off in different places depending on the domain. And then lastly, I took a look at one of these linear regression problems and did some calculations.